Let's see how to compute the capacitance of a 3D device. We'll consider a very simple parallel plate capacitance here because the analytic formula is well known. So let's consider a cylinder. For simplicity, we'll take a radius 1 and we'll take a height of, for example, 0.1 meter. Now, we will assign materials. Here again, for simplicity, we'll consider that it's an air parallel plate capacitor, just because the analytic formula will be very easy like that. Now we add the electrostatic physics. In steady state, it applies on the whole volume, and we apply, for example, a constraint of 0 volt at the bottom. This phase we have the ground. Now, to compute the capacitance, we need to apply a voltage and see how much charge accumulates, or the charge and what's the voltage. So both ways are possible. So for that we add a lump interaction. We add it to this surface, and then we can choose either we apply a voltage and then we'll check what's the charge and we'll divide and we will know the capacitance, or we apply a total charge and we'll check what's the voltage and we'll also get the same value of the capacitance. So both are possible. We could, for example, go for a charge of 1 coulomb. Here, just 1 for simplicity. That's it. So now we can go on to the simulation. We might want to see the electric potential field, and otherwise we will provide a mesh, and we might want to refine the mesh. In this case, the formula is very simple. We'll get very good accuracy even with a quite coarse mesh, but just to be able to capture nicely the curved geometry. Now, we could have a look at the script. We don't need to change it here, but you see the script that is automatically generated from the graphical user interface is extremely simple, and you can edit it the way you want to automate anything, or add anything in a quite convenient way. Now here we'll just do everything graphically, and we will also want to add a custom discrete output. So here, what do we want? We want to get the capacitance. It is the charge divided by the voltage on the top electrode. Now if we do this change, then we have to refresh the script, otherwise the previous script will be run. Now the mesh is finished. This is the mesh we're going to use, and we can run the simulation. So here it's a very small simulation. We don't need to do any acceleration. It will just run fast enough. Now the simulation is done, and we will see in the logs our capacitance value. Now, if you use the parallel plate approximation, so the permittivity of the air times pi times the radius square, which is 1 meter here, divided by 0.1 meter, you'll get 2.781 e minus 10. So this is really close, and the only reason it's not exactly the same is because the curvature is not perfectly captured with the mesh we used. So this is, anyways, extremely close to the analytic value.